Welcome back to the course, Multi-Layer Neural Network Training and Testing Implementation. This is Lesson 6, where we will discuss in detail the source code implementation of the training and testing presented in previous lessons. In this lesson, we will analyze in detail the C# source code that implements the training and testing presented earlier in the course. First, an overview of the neural network Visual Studio solution is briefly discussed. Then we will discuss the projects in the solution. This lesson will go into detail about how the projects and source code perform the following three functionalities: test setup generation, training of the neural network, and testing of the neural network. Use the GitHub URL shown in the slide to perform a git clone or download the zip file. If you are only interested in running the neural network executable, the GitHub URL to the latest distribution is shown as well. We will now go into detail about the source code. Once the source code is downloaded, open the neural network solution in Visual Studio. Visual Studio 2022 Community Edition was used for development, and the C# code was written using .NET version 7. As you can see, the Visual Studio solution contains 6 projects: the neural network executable, the test setup library, the samples generator library, the neural network library, the test functions library, and the utilities library. The test setup library is used to read in a training and testing specification. The samples generator library is called by the test setup library to generate the sample sets used in training and testing. The neural network library is the core project containing the code to train and test the neural network. The test functions library is a user-defined library that is used by the neural network library for specific use cases. The utilities library is used mainly to provide static methods to print matrix and array values, but it also contains the methods to generate random sequences and numbers. This library will not be discussed in any further detail. The main project is the neural network executable that orchestrates all the test setup, loading, and then the training and testing of the specified neural network. This is the main method in the neural network executable. The resulting neural network.exe program takes one argument, which is the path to the JSON test setup file. After successfully loading the test setup and generating the training and testing sample sets, the program will create a neural network with the specified configuration and then call the train method to train the neural network. Then it will call the test method to perform the validation, and finally call the user-defined method to summarize the test results. Before discussing in detail the source code for the test setup generation, let's review the structure of the neural network that was discussed in Lesson 2 so that you can recall all the parameters used in this lesson and the source code. A neural network consists of L neuron layers indexed from 0 to L-1. Each layer L has a matrix of connection weights labeled W superscript L, a neuron bias array labeled B superscript L, an activation function labeled alpha superscript L, and an output array labeled A superscript L. The first layer, layer 0, is connected to the N inputs, and the last layer produces the M outputs of the neural network that can be compared to the M targets for a given input array. The test setup library includes the test setup reader, which reads in a JSON test configuration file, generates the training and testing samples, and returns a test setup object to the main executable. The test setup specifies all the details of the neural network structure and its training and testing. Any number of neuron layers can be specified in the test setup JSON configuration file, including the activation function to use for each layer. The test setup class is the template for a specific test configuration. It specifies the structure of the neural network shown previously, as well as the specification for the training and testing sample set. It also has a definition for the random number generator used in all initializations. Importantly, the test setup contains the definition of user-defined functions that are used by the neural network for specific testing use cases. The test setup reader class is used to read in a test setup and works with the specified samples generator to generate the training and testing samples. The test setup reader's test setup class is a class corresponding to the test setup class. It specifies the configuration values used to set the resulting test setup object, as well as names of user assemblies loaded at runtime, the samples generator to use, and the name of the class for the user-defined functions used by the neural network code. Here we see an example test setup JSON file. As you can see, the keys in the JSON match exactly with those in the test setup reader's test setup root class. The JSON in the file is deserialized directly into an object which is then processed. In addition to reading in the neural network configuration, the test setup reader calls into a samples generator to generate the training and testing sample sets. The specific samples generator that is called is specified in the file. The code expects at least one generator to be specified. The generator's getSamples method is called, and the resulting samples are set in the test setup object. The samples generator library is used by the test setup library to read from a file or generate from a function the data records, and then divide the records into the training and testing sample sets. The library defines a samples class to store the training and testing samples, an abstract samples generator class, and two actual samples generators. The samples class stores the training and testing samples. The constructor receives the records and the fraction of the records that are to be allocated to the training set. If a random number generator is passed into the constructor, the order in which the records are selected to be in the training or testing set is random. Otherwise, the records are added in the order in which they appear, first to the training set and then to the testing set. The abstract samples generator class provides some default behavior for generating the training and testing sample sets from the data records. However, the manner by which the data records are obtained, the samples generator parent class does the division into the sample sets. The file samples generator class getSamples method reads the data records from a file. A specified number of rows and columns can be skipped when reading in the data records, and the separator between the values can also be specified. If a random number generator is passed in, the data records read in from the file are randomized in the order as discussed previously. The read records from file method reads in the data records line by line. The data records are stored in a list. The first number of rows to skip are ignored. Then each line is split by the separator, skipping the first number of columns. If it is the first line of values read in, the number of values is saved. Otherwise, the values are added to the list of records. Finally, the records in the list are transferred to the records array, which is passed to the getSamples method. The function samples generator class getSamples method generates a specified number of data records from a specified function with an arbitrary number of inputs and outputs. The input values are chosen randomly within specified ranges. The generateRecords method iterates through all the data records generating random input values, calling the generator function to produce the output values, and then copies the input and output values to each record. Because the records are generated randomly, they do not have to be randomized when creating the training and testing sample sets. The test functions library is a user-defined library of functions that are used for processing test results and the functions to use for sample generation. Note that although it is included in the folder, it is not used directly by the neural network code. The assembly must be specified in the JSON configuration file and is loaded at runtime. The intent is to provide an example of how to have access to external code in the neural network library. The user-defined functions interface defines the methods that the neural network code calls that must be implemented by a user class. The methods are configure, which is called before any processing to initialize any data structure. The compute errors method, which is called during training and testing to compute the difference between the neural network outputs for a given sample inputs and the targets for those inputs. The process test result method is called to allow the user code to process the results of a test. And the summarize test results is called after testing to allow the user code to summarize the test results. Here we see that the index of max matches class implements the user-defined functions interface. This implementation is used for classification problems where the targets are binary class vectors. That is, the targets and outputs represent an array of binary values where the value 1 is the index of the class. In actuality, the output from the neural network will not be binary, so the value with the maximum value is chosen to have the value 1 and all others will be 0. The ABS error class also implements the user-defined functions interface. However, this class is used for regression type prediction problems. Essentially, this class maintains the sum of the absolute values of the differences between the target and output values so that in the summarize test results method, the average absolute error is displayed. At this point, the test setup has been read in and created. It contains the neural network configuration as well as the training and testing sample sets. The main method then creates the neural network given the specification and calls the neural network's train method to perform the training. The core of the solution is the neural network library. This project contains the neural network class, the neuron layer class, and the activation functions interface and some activation function class implementations. As you can see, a number of activation functions have been implemented. You can add your own implementations and have them loaded at runtime by specifying them in the test setup file. The neural network class contains the definitions for the L layers and defines the train and test entry points called by the main method. The constructor creates the neural network layers from the configurations passed into it. The neural layer class contains the core logic for performing the training and testing. It contains the code for performing the feed-forward processing of the inputs, the computation of the errors by calling the user-defined function, the backpropagation of the errors, and finally the updating of the weights and biases. The entry points in this class are compute outputs, compute errors, and update methods. Before discussing in detail the source code that implements the training and testing, we will review the diagram that shows the computations occurring at an arbitrary neuron K in layer L. Each neuron in a layer is connected by weights to either the inputs to the neural network or to the outputs of the previous layer. The inputs to the neuron are labeled as A superscript L minus 1 sub j, with j going from 0 to n sub L minus 1 minus 1. Their corresponding weight is labeled W superscript L sub k comma j. In addition to the weights, each neuron has an associated constant called the bias for the neuron, which is labeled B superscript L sub k. In order to calculate the neuron's output, we sum the multiplications of each of the neuron's weights by their corresponding input, and then we add the neuron's bias. This operation is assigned for simplicity to a variable labeled Z superscript L sub k. This value is referred to as the net value. The output from this neuron is labeled A superscript L sub k. The net value is passed to the layer's activation function labeled alpha superscript L to compute the neuron's output for a given input vector. The activation function is specific to the layer. Each layer can have its own activation function, or all layers can use the same activation function. Before discussing the source code that implements the neural network training, we will review the training process. Training is performed for each sample consisting of an input array X and a target array T. The first step in training is to compute the output array Y for the input array X. The second step is to compute the error between the actual output array Y and the target array T. The error function is user-defined. The third step is backpropagation, or the computation of each layer's errors starting from the last layer back through the neural network to the first layer. The fourth and final step in training is the adjusting of the weights and biases based on the inputs and errors into each layer, a process called gradient descent. This slide is a review of how the input array X to the neural network is processed through all the layers of the neural network to compute the output array Y from the neural network. The output array from each layer, denoted by A superscript L, is computed from the outputs of the previous layer or the inputs to the neural network. Starting from layer 0, the inputs to the neural network are processed and propagated to the last layer of the neural network. The last layer of the neural network computes the output array Y from the neural network. The neural network's train method is the entry point for the entire training process. As shown previously, this method is called by the main method of the executable program. The training is divided into the specified number of iterations, or epochs. The order in which the training samples are presented to the neural network is randomized for each iteration. The order, or sequence, is calculated by the generate sequence method in the utilities library. Then each training sample is processed one by one. For each training sample, the compute outputs method is first called, followed by a call to the compute errors method, and finally to the update method. The neural network's compute outputs method is called for each training sample with the sample's inputs array as parameter. This method iterates through all the layers starting from the first layer through to the last layer, calling each layer's compute outputs method. The outputs from each layer become the inputs to the next layer. The outputs from the neural networks are the outputs from the last layer. The neuron layer's compute outputs method calculates the layer's outputs from the inputs. The inputs are first saved to be used later to update the layer's weights and bias. As discussed previously, each neuron's net value is calculated by summing the product of an input with its corresponding weight and then adding the bias value. The net value is then passed to the activation function to compute the neuron's output. This is done for every neuron in the layer. Finally, if the activation function implements the post-process method, the outputs are processed by that method before being returned. After obtaining the outputs for the sample inputs, the user-defined compute errors method is called with the sample's target and the neural network output arrays to compute the errors. As you can see, the user-defined compute errors method calculates the error to be the difference between the targets and outputs. After the errors are computed, the update method is called with the errors to initiate the updating of the neural network's weights and biases. As you can see, the updating starts from the last layer back to the first layer. For each layer, the errors that are fed back to the previous layer are calculated, and then the layer's weights and biases are updated. Here we see how the errors passed into a layer are used to compute the errors passed back out to the previous layer. For each of the layer's neurons, the derivative is first calculated, which is then used to calculate the neuron signal array along with the input error array. After all the neuron signal arrays are calculated, the errors passed back out to the previous layer are calculated by multiplying the signal array with the transpose of the weight matrix. After the errors for the previous layer are calculated, the layer's update method is called to adjust the layer's weights and biases. It is in the neuron layer's update method where the weights and biases are adjusted. Gradients and deltas are calculated, and are then used to adjust the weights and biases gradually using the training rate and momentum parameters passed into the method. Now that the neural network has been trained, it's time to validate the training. To do this, the main method calls the neural network's test method with the testing sample set. The testing proceeds as follows. For each sample in the testing set, forward propagate the testing sample's input array to compute the output array. Then call the user-defined method with the input, target, and output arrays to process the test result. This is the code that performs the testing. For each testing sample, call the compute outputs function. Then call the user-defined process test result method with the inputs, targets, and computed outputs. This code is a user-defined functions process test result method, which is called by the neural network's test method for every test, passing to it the sample input, target, and computed output arrays. This example is for a classification prediction problem where the targets and outputs are binary class vectors which, as we discussed previously, has 1 at the index corresponding to the class and 0 at every other index. This process test result method computes the index of the maximum value for both the targets and the output arrays, and then checks to see if they are the same index. If they are the same, then the test is considered passed. For each sample, all the arrays are printed out along with the result of the test. You can implement any method for your particular use case. Finally, the main method calls the user-defined summarized test result to do any processing to or displaying of the test results. This example of the summarized test results method simply prints out the overall classification prediction accuracy, which is simply the average of all the tests that passed. As with all other user-defined methods, you can implement any functionality for your particular use case. This concludes the analysis of the source code. In the next lesson, we will be discussing testing with data sets.